This is Magic 063 Differentiable Manifolds. I'm Dm Kchm, and this is the second podcast on vector bundles. This is mainly about algebraic constructions with vector bundles. So the best way, most of the time, is to think of a vector bundle as a parametrized family of vector spaces, parametrized by the points of the base manifold. And given that, it's reasonable to think that if you're doing something standard algebraically to each vector space, to each fiber of the vector bundle, and that's a construction that's natural, first of all in the ordinary sense of the word, and secondly in the categorical sense of the word, then it will be uniform across the base manifold and will give you a construction for the vector bundle. There are exceptions. We'll talk about one much later, but this process of applying the standard construction fiber-wise works a great deal of the time. So I'm going to deal with two examples of these, and the first one will be the direct sum of two vector bundles, written with the plus sign. And this is often called the Whitney sum, particularly when you need to emphasize that we're taking the sum of the bundles, we're taking the sum of the fibers, fiber-wise, but we're not doing anything to the base manifold. E1 is on base M, E2 is on base M, and the Whitney sum is on base M. It's quite possible to take the product of two vector bundles, indeed on different bases, and have a base that's the product of the bases. That's an entirely different construction. I won't talk about that here. So what we want in this case is a vector bundle on E for which each fiber is equal to the direct sum of the fibers of E1 and E2. And there's something to watch out for. For vector spaces, as I'm sure you know, there's not a real distinction between the direct sum and the direct product. So we can write the direct sum equally well as a direct product, and we can write elements either as pairs from V1, V2, like coordinates in R2, or indeed as direct sums like that. And each has its particular strengths, and in some situations one will be better than the other, but they are pretty well interchangeable. So here's the process. I'm not sure if I actually wrote down, but what I have in mind, of course, is that the fiber of the Whitney sum over M will be the direct sum of the fibers. That's implicit in what I've said already. And put that differently, by E1 sum E2, at the moment I just mean the disjoint sum of all these direct sums. So it's a disjoint sum of vector spaces. It's not yet a manifold. We'll put vector bundle charts on this set, and that will provide a manifold structure as well. So I take charts for E1, and I take charts for E2. And of course, in general, if I take a system of charts for two different vector bundles, even on the same base, then the open sets U alpha will be different in one bundle from the other. But I can easily assume that it's the same, because I can take any point of the base manifold, and around that I can find a U alpha 1, say, for the vector bundle E1, and a U alpha 2, or perhaps some other subscript U beta 2, for the second vector bundle, and then I can restrict both to the intersection. And in that way, I get a system of vector bundle charts for E1 and E2 using the same open sets U alpha of M. So that's a simplification to start with. And here we are. E1 direct sum E2 is the set union, the disjoint union of the various direct sums of the fibre spaces. And I define charts, psi alpha, for this system. In the obvious way, I take U alpha and then the product with the direct sum, V1 and V2, and I map that over to the union of all the E1M direct sum E2Ms, where M is in U alpha. And the chart, the psi alpha, is the obvious thing, that in the first coordinate it's just the psi 1 of alpha, and in the second it's psi 2 of alpha. So that's simple and natural, and I'll leave you to check that this really does define a vector bundle structure on that disjoint sum of direct products. So you need to calculate the overlap maps and check that they behave properly for a vector bundle structure. And in the process, you'll find the transition functions for the system of charts that we started with. Okay, so that's a slightly messy thing to write down, but I think you'll find it's quite straightforward. So also, you should check that the projection maps, here they are, simply projecting onto the first factor and the one that projects onto the second factor, are morphisms of vector bundles. And indeed, that's extremely straightforward. And likewise, the injections, that I inject E1 into the direct sum simply using 0 in the second factor. Perhaps I ought to put a little 2 on that and a little 1 on that, to that these are also vector bundle morphisms over M. So that's actually all the standard properties of a direct sum, and as I say, it's straightforward. Here's the second example. It's the Hom set for two vector bundles, again on the same base. And this time I'm going to write V1 and V2 for the fibre types. In fact, I did that already in the previous construction. It's slightly more manageable than using Euclidean spaces. So Hom, I write Hom of E1M, E2M for the vector space of all the linear maps from E1M to E2M, standard concept. And I write Hom E1, E2 for the disjoint union of all those individual spaces, depending on M. And I write Q for the map that sends an element of Hom at M to the point M. So again, I need to define charts for this Hom, this one here, and I can assume that there are charts for E1 and E2 that are over the same open sets U alpha, just like in the preceding construction. And I need to define a map from U alpha cross Hom V1, V2, the fibre types, to Hom E1, E2 restricted to U alpha in the same way. And there's the formula, and I think it's reasonably straightforward. Remember, H is going from V1 to V2, and psi2 alpha m goes from V2 to EM, E2M, and psi1 alpha m inverse goes from E1m to V1, and so the composite is this map, the fourth side of the square that goes from E1m to E2m. So it's the completely natural thing to do, and it works. And again, I urge you to check the details and find the transition functions. So one thing to note is that, of course, the dual of a vector bundle is a special case of what we've just done. The dual is indeed simply Hom of E m cross r as the first use of a trivial vector bundle, right? And it's not a bad idea to write that case out as a particular special case. Now, one can do the same sort of thing with exterior powers, or, of course, indeed, any finite number of variables. Tensor products, any of the standard algebraic constructions will go through. I should mention, since I'm talking about all or almost all things going through very quickly, one thing that you do need to be careful with is quotients. And I'll talk about that in a different context later on. So that's one thing that needs care. But virtually everything else does go fibre-wise to arbitrary vector bundles. So then there's the canonical isomorphisms. Here's a typical one from Hom, VW, these are vector spaces, to V dual tensor W, or perhaps it's better to take it in the reverse direction. But that's an isomorphism, and it's a canonical isomorphism of vector spaces. And this also carries over to vector bundles. And we can prove that if we've got two bundles, E and F, then the Hom vector bundle is canonically isomorphic to E dual tensor F. So I'll sketch the method, and again, I'll leave the details to you. First of all, write R0 for the map that goes from V dual tensor W to Hom, and that's defined on generators like that. Okay, so the elements of the tensor product are generated by these simple elements, epsilon tensor W, where epsilon is in V dual and W is in W, and one extends by linearity in the natural way. So R0 of epsilon tensor W is going to be in Hom EF, so, I beg your pardon, Hom VW. So I apply it to an element little v of V, and what I get out is the element W that I've been given times the pairing of epsilon with V. Okay. And I expect you know that does give an isomorphism of finite dimensional vector spaces, and it's canonical in the sense of category theory. So write Rm, R sub m, for the corresponding map on the fibre over M. Okay, and then define R to be essentially the union of all these Rm. And the only real job is to prove that R is smooth. And the way to do this is to take charts. For Hom, we've seen how to do it. For the dual, you can check easily enough how to do it. We haven't done tensor products, but it's a straightforward modification of the direct sums that we did do. And once you've got charts for the domain there and charts for the target, you can show that with respect to them, constructed in the same way, the map R turns into, well, first of all, it turns into a map like that, from U alpha times the fiber type of the domain to U alpha times the fiber type of the target. And what it actually is simply that. In fact, it would actually be easier to write down that it's the identity on U alpha times R0. And that gives you smoothness immediately. So again, that's a check, and I recommend it. So apropos the previous slide, the same process holds with the other canonical isomorphisms that are present between the various natural constructed vector bundles. This frame, this slide, is about vector bundles in general. It's a definition that you probably know. The definition of a section of a vector bundle is a smooth map from the base manifold into the vector bundle space, which is right inverse to Q, that's the bundle projection. Let's write it down. Sends each point of M to its base point, so that mu of M is in EM for all M in M. And of course, if E is the tangent bundle, then the sections are the vector fields. Vector fields interpreted as maps in this way. If the vector bundle is the cotangent bundle, then the sections are the one forms, again interpreted this way. And we've gone to some work to interpret sections of Tm and sections of T star M in more directly usable ways. But nonetheless, the fundamental definition is that they're sections of these bundles. Now go back to a general E, a general vector bundle E. The set of all sections is denoted gamma E. Some people write gamma infinity E. I'll just write gamma. Two sections, U1 and U2, mu1 and mu2, can be added pointwise to get another section, and they can also be multiplied pointwise by smooth functions on the base. And there are the two formulas. And again, they're just like the formulas that we used for adding vector fields and adding one forms in terms of sections of the tangent and cotangent bundles. So these make gamma E into a module over the smooth functions on the base. And again, it's finitely generated and projective. So it's a good sort of module. Okay. Now, I want to talk about morphisms of vector bundles, and throughout this part of the podcast, these morphisms are all base preserving. So let E1 and E2 be vector bundles on the same base M. If I take a section of Hom E1, E2, then what it's giving me is, for each point M of the base, it's giving me a linear map from E1M to E2M. And if I combine those together, this is rather like what we did with the maps RM a couple of minutes ago. If we combine these together, then they give a map from E1 to E2, namely that mu M is indeed this map on the fibres over M, and that is in fact smooth, and it's certainly a morphism of vector bundles. That's a straightforward thing to prove. You can ask me if you would like to, but it's a very straightforward result to prove. And that means, in fact, that sections of Hom E1, E2 can be identified with morphisms from E1 to E2. There's the converse here. If phi is a given morphism, and we look at the map that sends a point of the base to the restriction of phi m to the fibre over m, then that is again a smooth section of the Hom bundle. Okay. Okay, that's one thing. Now the next thing about morphisms of vector bundles is that if we're given a phi from E1 to E2, base preserving, then it induces a map on the sections just by composition. I take a section of the domain mu1 and I compose it with phi, and that gives me a section of the target E2. So I get a map from E1 to E2. Beg your pardon. I get a map from the sections of E1 to the sections of E2. And when we're being careful, we'll denote that by gamma of phi. But in fact, most of the time, most people drop the gamma and just use phi for the map on the level of sections as well as for the actual map of the vector bundles. This can be confusing, but it's a convenient terminal notation. So it's easy to see, it doesn't really need a proof. This map, gamma phi, is a morphism of C infinity m modules from gamma E1 to gamma E2. Because if I multiply mu1 pointwise by a function f, then it will simply come out through phi, because phi is a linear map defined fibre by fibre. And here's the converse, and this does require a proof. Let capital phi be a map from the sections of E1 to the sections of E2, which is a morphism of C infinity modules. In other words, function linear. Okay. Then there's a unique morphism of the vector bundles that's on the level of the fibres, which induces capital phi. It's not a particularly hard proof. It depends on having bump functions, and therefore it depends on the paracompactness assumption that we made about the underlying topology long ago. But once you've got that, it's a straightforward result. So that is the result that gives us the extension to arbitrary k-forms of the various equivalent formulations that we've had for one-forms. So if I take E1 to be Tm, tangent bundle of the manifold, and E2 to be the trivial bundle m cross r, we get the correspondence between one-forms as C infinity m linear maps, function linear maps, from vector fields to smooth functions. That's on the one hand, and one-forms as maps from the tangent bundle to the reals that are linear on each fibre. And that, of course, is very close to sections of the cotangent bundle. So we extend this to two forms, and I'm going to do it like this. We'll take E1 just to be the direct sum of two copies of Tm, and E2 will still just be the trivial bundle m cross r. Sections of Tm, direct sum Tm, are pairs of vector fields, and we could write x comma y in brackets, or we could write x direct sum y. And as with vector spaces, whichever notation you use, you can write these as sums of individual elements. So using the direct sum notation, x sum y is x sum 0 plus ordinary sum 0 sum y. So the module of sections of Tm sum Tm can be identified with pairs, the direct sum of two copies of the module of vector fields. And we could think of that as a direct product if we like. Okay. Notice I'm not talking about an exterior square. I'm just using the direct sum, and I'm imposing, or I will impose, the condition of being alternating as needed for differential forms. My intention here is to bypass all the construction that's needed for the exterior power bundles. That's something that everybody needs to look at sometime, but you can go a very long way working with the formalism as I've set it up in these podcasts and the live sessions. And I think that's the important thing, to get used to working with differential forms and vector fields and all the other apparatus. And at some point you will want to sit down with one of the many good books that there are and work through the actual construction of those exterior powers. But I'm not going to do that now. So there we are. It's possible to construct such a bundle for which the sections correspond precisely to the two forms, but I'm just working with the formulation that I've given there. So, of course, that extends to K-forms in an immediate fashion, and I'll use both formulations for K-forms. So now, just to emphasize the important thing, we'll use both formulations of differential forms. So rough description will be differential forms as defined on vector fields and differential forms as defined on tangent vectors. And there's a word missing here. It should say when working with maps of sections. I'll rewrite it more neatly out there. When working with maps of sections, the distinction between maps that are linear over functions or multilinear over functions and those that are not is crucial. So if you do have a map of sections that's linear or multilinear over functions, then in fact it corresponds to a map that you can define on the level of the bundles, on the level of the tangent vectors. But if it's not linear, if you've got nonlinear terms or what are sometimes called Leibniz terms, then that's not the case. And a clear example is just the exterior derivative going from zero forms to one forms. The zero forms are the smooth functions, and they're the sections of the trivial bundle. And the one forms, of course, are sections of the cotangent bundle. But D does not correspond to a vector bundle morphism from the trivial bundle to T star M. Okay. It's not function linear, and therefore it can't be defined on the level of the actual bundles. It can only be defined in terms of sections. And that's true of all differential operators, except, I suppose, differential operators of order 0. And a differential operator of order 0 will normally be a function linear map between vector bundles. But for order 1 and above, that's where you really do have derivatives involved, then a differential operator won't be function linear. Okay, that's all for now. We will come back to vector bundles again in the future, but the next couple of podcasts are to do with different aspects of what we've been doing.